chemical transport ni orang dan bergerak dalam tanah ni ada banyak benda. Contohnya chemical yang contohnya kamu punya rumah ada apa? Ada apa chemical? You ada Milo kat rumah. Milo tu air minuman, tapi dia boleh larut dalam air. Kalau dituang air Milo tu dalam tanah, dia akan bergerak dalam tanah. Dia bergerak secara mencancang dan juga mengufuk. Tapi disebabkan ada daya tarikan graviti, dia bergerak ke bawah lebih mendalam. Okay. Alright. So apa lagi benda yang boleh larut dalam air? Contohnya kalau you pergi ke kawasan sawah padi, ke kawasan pertanian, dia ada guna banyak baja, fertilizer. They also use pesticide. So all these things can be dissolved in water and transport in the soil if you apply it to the soil. Especially when the rain comes, the rain would dissolve these chemicals and move downward.
Ke mana?
Okay. All right. So there are some other things. For example, spillage. For example, there's an accident. So the accident involves the spillage of oil or the spillage of this petrochemical on top of the soil. As a result, this chemical can move and transport down into the soil. So that also falls under chemical transport in the soil. So it can be much more than that. Salt, for example, garam, okay, salt can also transport in the soil. All right, so today we're going to look into the equations that govern this kind of transport in the soil. All right, so in general, you have a PDE that can be written in this form, right? JC. Right. So the CT itself is the total concentration. Then you have this JC is chemical mass flux. Okay. And then you have this RC is the mass loss. If its sign is negative, it's a mass gain. If it's positive, so you can see the sign can be positive or negative. So positive means mass gain, negative means mass loss. So you have a cube, solute coming in and solute move out. So the CT is within here, and the flux is this, the JC coming in and the JC going out. And then within this, you have a RC. RC can be positive, can also be negative. All right. All right. So it can be positive, can also be negative. All right. So the in and out JC is governed by this term. The degradation or bioproduction is governed by this RC, and the storage is actually happening here. So this JCT dt, the storage is actually happening within the storage area. All right. So maybe it can be written as JCT dt. Okay. All right. So let's look into this. What is CT exactly? Okay, what is CT? All right, let me just remove this so that just focus on here. So what is CT? CT is given by the bulk density, okay, the CA. All right, volumetric water content, right, concentration in the water, air porosity, and CG. All right, the concentration in the gas phase. So you have here, you have a solute means chemical in solid phase. So how is that chemical in solid phase? Means the chemical actually attached to the solid. Then you have Cl, this theta WCl, this is solute in liquid phase. Then you have a solute in gas phase, right? So here we have equation 1, all right? And then here we have equation 2, okay? Then now we'll look into JC. What is JC? The flux, okay? The chemical max flux. So max flux basically means movement, all right? So you have JL plus JG, right? JL and JG. So JL, okay, the JL itself, is contributed by JLC plus JLH plus JLD. So what is that all about? JLC, okay, then we have another one, so JG, yeah, okay, JG. So you have this JL can be broken down into these 3 terms, okay, right? Okay. Now, JLC is solute transport. Is a solute transport. Or we call it solute flux, okay? Better description is solute flux in liquid phase. Okay. And liquid flux, actually the most accurate term to describe this is solute flux by bulk flow. Okay. JLD is solute flux by hydrodynamic dispersion. Okay, SION. And then JLD, okay, JLD is a solute flux by diffusion. Okay. And then this JG is solute flux in gas phase in the forms of diffusion. All right. So you see, if you go and look at water, if you go to a river side, look at the river flow, right? You can see the river flow from top to bottom. That flow of water in the river is called bulk flow, okay? Bulk flow, okay? That's what you get JLC. And then at the same time, you can also see in the river, let's say if you take an ink, you drop in the river, and the river will move together with the water. Sorry, if you take the ink, you drop into the river, the ink will move together with the river. Sorry, okay? It will move together with the water in the river. So when you drop an ink inside the water in the river, the ink will move together with the water in the river. That movement is called bulk flow, okay? Bulk flow. And then if you take the ink, you put in a glass of water, you can see the ink not just not moving, but it's actually spread. The spreading of the ink in the water that is not moving, means the water is in stagnant. If you take the ink, you drop in the water, you can see the ink spread homogeneously. If you wait long enough, the ink will be spread throughout the whole water. That kind of movement is called diffusion. So when the water moves, the water carry the solute, but at the same time, when the solute is in the water move, the water will carry the solute. But at the same time, the solute in the water is also spreading out. That kind of spreading is called diffusion. When the water moves, the ink moves, that is called bulk flow, or sometimes we call it advection, convection, okay? But here, I write here as a bulk flow, okay? But you must know that bulk flow, advection flow, they are all convection flow. They are referring to the same thing. And then apart from that, since the solute is travel in the soil, there is another phenomena, they call it hydrodynamic dispersion. Okay, hydrodynamic dispersion. Hydrodynamic dispersion is just used to indicate that there is a discrepancy, wujudnya ketidaksamaan di antara pemerhatian dan juga eksperimen, pemerhatian dan juga teori. So teori tak boleh nak describe, teori maksudnya persamaan. Persamaan tak boleh nak describe tak boleh nak describe pemerhatian. Okay, tak boleh nak mewakili pemerhatian. So what it means that the theory, the equation cannot describe the observation from the experiment. So it means that there is some kind of discrepancy. There's some kind of unequal observation. Means the theory cannot describe the observation. Something is missing. So the missing observation, they introduce hydrodynamic dispersion to describe this kind of discrepancy. So hydrodynamic dispersion is a result of correction, okay? Correction between experiment and theory. And then this solute, not just present in the liquid, they can also present in the forms of gas. Take for example, if you have petrol. When the petrol get into the water move. The petrol will move with the water. At the same time, the petrol will also spread out due to diffusion. Also, the petrol can be evaporate. When the petrol evaporate, it will move into the gas phase. So the petrol in the gas phase in the soil can also diffuse. That's why you have a diffusion in the gas phase, right? So that's basically what it means. Okay, so JG, okay, the gas phase diffusion is given by DG as ECG. Is that okay? And then JCL. And then we also have JLC, ADG. We also have this JLC. JLC is given by JLC is given by JW CL. Okay. DLH. JLH is negative. DLH. DCL over DZ. And then this DLD, JLD is given by negative DLS. DCL, DZ. Okay. Then of course this JG is coming from here. Okay, JG. So we can rewrite this equation. JC equals to JW CL minus DLH DL DZ DLH sorry DL SH DCL DZ, right? And also negative DGS DCG DZ, okay? And then can be simplified as this. it can be simplified as dE Cl dz es dg z dz. Okay, so this is basically the combination of these two become this. Okay, it's just a combination. All right, and this dE is what we call effective diffusion dispersion. Okay, and then now we have this is equation 3. Okay, equation 3. Now we have talked about CT, JC. Now we want to talk about RC. Okay, RC. RC is the reaction, chemical reaction. It can be generation, it can be degradation. So generation means it produces the solute, it produces the substance. Degradation basically means the substance degrade over time. It lost the mass over time. All right, so RC is given by rho B RA. We already, okay, not yet stated. Del W RL plus ARG. All right, so this is solute mass loss rate in solid phase. Okay, and this is solute mass loss rate in liquid phase. So this is solute mass loss rate in gas phase. Okay, so you have 3 phases. Now this is what we call this is the equation we give it number 4. Now we have 4. We have equation 4. We have equation 3. We have equation 2, and we have equation 1. Now what we want to do, we want to take equation 4, equation 3, equation 2, and replace it into equation 1. Okay, so we want everything enter into equation 1. Right, so in this case we will get right, we get something like this. So if there is negligible vapor phase, so means no vapor phase, so means the solute, it does not convert from liquid into gas. So something can be simplified, so it can be simplified until this form. Okay, it can be simplified like this. You see the gas part, we remove the gas. Okay, we remove the gas. Okay, so we remove the gas. We can also make another simplification. Say, for example, if we say solute is non-absorbing. Okay, non-absorbing. All right, so what does it mean? Non-absorbing basically means the solute does not attach to the soil. Okay, it does not attach to the solid phase. So means Ca is 0. So it means this Ca is 0, right? Okay, because Ca is actually the solid phase. So the solute does not attach to the soil. So what if solute non-reactive? So they means that they are non-reactive. They cannot generate. They also cannot degrade. So basically mean Ra equals to Rl equals to Rg equals to 0. So they are all 0. So means they does not appear. Okay, they can be cancelled out. Okay, that's what it means. Can be cancelled out. Okay. So no reactive means no degradation, no degradation, no bioproduction. Okay, no degradation, no bioproduction. So if it is also non-volatile, non-volatile means they cannot evaporate. So if it cannot evaporate, means the Cg, okay, in the gas phase is also 0, right? So that means Cg can be cancelled out. Okay, so that what it means. Okay, that what it means. Cg can be cancelled out. All right. So now we can actually simplify this equation further. We will get something like this: d dt w cl AWCL minus DE CL dz. All right, so you can see from a very from this form, okay, from this form, if you say that there's no vapor phase, simplified, and we make a list of assumption, all right, and then it can be simplified further to get this. So from here can become like this. All right, like just making a series of assumption. Okay, then what we have here, you have storage, you have bulk flow. So means what? Bulk flow basically means the fluid is moving. So the solute move because the fluid is moving. And then you have this what we call diffusion dispersion. So means the solute actually disperse at the same time it is diffused. So as I mentioned to you, diffusion is something like if you have a pool of water that is not moving, you take a solute, you put inside. For example, you take an ink, you put in the water, and you can see the ink in the water that is not moving. The ink is spreading out from the middle. Where you drop it, it just spread out. So for example, this is this is water. You drop an ink inside here. Over time, the ink will spread. Okay, so it's spreading bigger and bigger, bigger and bigger. So that is called diffusion. Okay, diffusion. For mechanical dispersion, as I told you, this is correction factor. So you have a correction factor as a result of the discrepancy between experiment and observation. So dispersion is more like a correction, but it's also actually a phenomena. Okay, a phenomena that due to the presence of soil cause this kind of mechanical dispersion take place. All right. So can we simplify further? Can. So if solute has no dispersion, so we assume that dispersion does not exist. Okay, then what happens? This equation becomes dt w cl equals to dz w cl. That's all. Okay. Yeah. So it can be simplified further, right? So depending on the assumption we make, right? So the question is, having more assumption is good or not good? The answer is no. Having so many assumptions is not good because you are not more, you're becoming less realistic. To be realistic, you need to have all this. Okay, this is the most realistic. Okay, most realistic equation. That also means you need to provide all this information. But since you don't have this information that much, you can simplify it to the most easiest form. You get this, all right? But the question is, can you even simplify this further? The answer is yes. Assume assume oh, assume solute transport in steady state. Okay, that means become zero.
Doctor,
Yes.
sorry, Doctor. Turn off the screen.
Oh, screen disappear.
Oh, yeah.
So what do you see right now? Can you see? Can you see?
No. Oh, yeah, yeah.
Now can see, right?
Oh, yes.
Okay. Let me see.
Okay, Doctor.
Okay. So you can simplify further. You assume that solute transport in steady state. So it's steady state means there's no storage. Then you get something like this. JWCL. So that is exactly what it looks like in steady state. So if you have a solute coming in, going out. So JWCL coming in, JWCL going out. Inside here, storage, the CT equals to 0. Sorry. The JCT over time equals to 0. So there are no storage inside um, the system. Okay, so you can assume this as a system. All right. So that's basically how it looks like. Okay. So that's the simplest you can go. Right. So now let's look into an example. See how can we turn this into something that practical. So we can have a good idea. Okay, so we can get a reasonable grasp. I mean, get a reasonable idea how it might be looks like in application. Okay, so look at this question. Example 7.2. Calculate calculate the amount of time required to transport nitrate. Nitrate is a fertilizer that needs by the plant to grow. Okay, so to transport nitrate, a mobile anion from the bottom of the root. So you have a tree. Okay, so you have a plant. Okay, so there's a root underneath. Okay, maybe my drawing is not so good. Okay, okay, so you have something like this, roots from the bottom of the root to the groundwater. So you have a groundwater here. So the distance is 10 meter. Okay, and obviously this is soil. Okay, soil. The soil has a water content of 0.15 meter cube over meter cube. And then you have a average annual drainage rate. So you have a drainage of 0.5 meter per year. So the water actually moving down, okay, at this rate, 0.5 meter per year. So now the question is, can you calculate the amount of time? So want to find the time. Needed nutrient, anion, nitrate from here, okay, from here, let's go here. Why? Cannot change. Okay. Okay. From here to here. So how much time is needed? We need to find the time. All right, so we list out the information. We have L is 10 meter. We have theta W is 0.15 meter cube over meter cube. And then we have a D. Okay, the drainage rate is 0.5 meter per year. Right. Now, so we can find how much water actually in this 10 meter column of soil. We can do this simple calculation. L multiply with theta W, which is 10 meter, multiply with 0.15 meter cube over meter cube. What do we get? We get 1.5 meter, right? And then we want to find the time, right? So obviously we want to find the time. It's quite simple. We just take the dWb over d. So it's 1.5 meter over d. What is d? 0.5 meter per year. And then that should give us about 3 years. Okay, 3 years. Okay, 3 tahun. To flow from the bottom of the root to the groundwater, it takes 3 years to complete the transport time. So now, I would like to raise a question. How many assumptions? So how many assumptions made so that this calculation can be made possible? Okay, so you see, the original equation is this. Okay, this is the original equation. All right, it's a very complete equation, but also very it needs a lot of information. You need more information to actually find out the answer. But you can also do calculation as simple as this. So how many assumptions made for you to make this calculation? So you can see this problem is actually being solved by using just this equation. Okay, very simple. What's in, what's out, no storage. So the water here move down to here and no storage in between. That's what it does. So how many assumptions it makes? So the assumption is no. Okay, so you look at this. Do we consider any gas here? Gas flow? No. So we don't consider nitrate in the forms of gas, right? So obviously there's no non-volatile, no gas. Okay, non-volatile, volatile, there's no non-volatile, so it means Cg equals to 0. No gas. Okay, no gas. Is there any degradation bioproduction? No, we don't consider that. We don't consider nitrate to degrade here. So no reactive. Okay, no reactive. So basically means Ra, Rg, Rl 0. All right. Also, do you see any nitrate in a solid form in the soil? No, we don't talk about that. Okay. We also don't talk about that. So no absorbing solute. Ca in the solute in the soil 0. So these are the assumption. Ini adalah anggapan-anggapan yang dibuat supaya pengiraan yang mudah ni dapat dilakukan. So tiada nitrate dalam gas. Nitrate itu tidak melalui proses degradation. Tiada bioproduction. Nitrate itu tidak meresap ke atas tanah. Dia hanya berada dalam keadaan air. So Ca sama dengan kosong. So these are all assumptions. What else? What are the assumptions? Do we use any diffusion dispersion? No. So assume no diffusion. Okay. So DLS 0. Also no dispersion. So DLH equals 0. So if the calculation is so simple, there's no storage. So what does it mean? It assumes steady state. Or no solute storage. Okay, that's why we get D, T, W, PL equals to 0. So you can see here, this part becomes 0. All right, that's why you can simplify the whole thing, become like this. All right, so this is the assumption. All right, no storage. Or you can say that it's steady state. Steady state basically means no storage. All right, so with all these assumptions, if you look back into that equation, okay, if you look back into this equation, I'm going to copy. Okay, got it. Okay. Okay, so if we look back into this equation, we can see how we can actually cancel it out. We can see that CG, okay, CG 0, okay, okay, CG 0, so CG cancel out 0, okay, CG cancel out 0, RA, RG, RL 0, so 0, 0, 0. What else? CA 0, 0. Okay, what else? Diffusion, dispersion 0. So this is diffusion and dispersion 0. What else? No storage. Okay, no solute storage or steady state. Basically means this part 0. Right? So you can see that very simple. You just get this 0 equals to W JW CL. And this is exactly the calculation that we are doing here. Okay, that's how we do it here. Very simple. Simple calculation. All right. So I hope that's clear to you. I think that's all that I want to share with you for today. Let me see.